So okay, so we'll go into what the terminologies are. What are the kind of words that are used in graph, like when you represent graphs? So essentially, there are a few things. One is we have nodes in a graph. So nodes are, you can imagine, as certain abstractions or structures that can hold information in. And we'll go through an example as well, where we'll define what are these different elements. And what are adjacent nodes? So adjacent nodes are nodes that are close to each other, and in a graph, nodes are connected through edges, right? So adjacent nodes are nodes that are connected through edges, and not adjacent nodes are those nodes which don't have any connection between them. Edges basically turn to be links. So a graph is basically a linked connected data structure. So you would have multiple elements that are linked together by some relationship, and edges basically define the relationship between the nodes. So you can imagine them as being like directed or undirected links between these nodes. Then certain graphs can have weights. So weights basically, or labels, are essentially given to nodes in a graph, which can show or depict the importance of nodes right, of the importance of nodes. So essentially, let's say if you're building a graph which is connecting roads between different houses, the weights could indicate like how many people live in that particular house, right? So essentially, roads that connect a lot of nodes with high amount of weights is basically where a lot of traffic could be, right? So just those kind of semantics can be embedded using weight as an idea. And labels can be used to just identify nodes uniquely. So there are different use cases for this. Node set is essentially set of all the nodes. So collection of all the nodes represented in an array or a set could be just called a node set. Edge set is just collection of all the edges. A directed graph, so graphs can be different types as well. You can have directions between them. So a directed graph would basically indicate that there is a certain relationship between nodes. So if you consider a family tree, there would be a direction from grandparents to parents to children, right? But if you consider, for example, a road, then probably there is no direction, because roads are unidirectional. So you can have like, bidirectional, right? So then they would not have any direction. So undirected graphs are graphs which don't have any direction in them. And then there are two other types of graphs as well. So essentially, there is this cyclic and a non-cyclic structure to a graph. So a cyclic structure is where you have a graph where if you start from a node and you follow a path in a directed graph, you would come back to that particular node. So it will have cycles, and an acyclic graph will not have cycles. So essentially, any tree that we kind of discussed in a few lectures back is pretty much an acyclic directed graph. Cyclic graphs could be just roads as well, because roads can be like circular and you can come back to the same node from where you started, right? So different types of graphs. The most important terminologies to remember are just like nodes and edges, and those usually constitute most of the problems, right? So example usages could be that you just need road connections between city 1 and city 2, and there's a highway in between. So highway basically represents a direction of movement from city 1 to city 2. So it could be a directed graph as well, right? Family tree representation, thereby father and mother, and they have a child, a relationship with a daughter, right? So this tends to be the nodes, and this is pretty much like the label on the node, and this is the name of the relationship between the nodes. Then representation of graphs is something that is kind of interesting, in a sense that when you're given any graph problem, right, you are not given how you want to represent that graph. And this was something I used to have some trouble with, just understanding how can you represent a graph, because the visualization will be probably with nodes and links, but the way you represent could be in different types of data structures. So there are three major representations that are used in graphs. So the first is pretty much an edgeless representation. And so the idea with an edgeless representation is that, let's say you have a graph which is A pointing to B, B pointing to C, and A also points to C. And these are the three nodes, so 1, 2, and 3, which are the labels associated, or IDs associated with those nodes. The way you can represent is you can have an array, so a two-dimensional array, and and the array could have each row in the array could have three elements. So the first element would basically indicate what the current node is. So let's say you're just representing A in this first row, and then the first would basically represent A. The second element would basically represent a collection. So collection of nodes from which A has a directed link. So in this case, A has a directed link to B and C. So this represents B and C, or 2 and 3. So they are basically the same identifiers. And the third node basically, or the third element in this array represents the nodes from which there is a link to A. So in this particular example, A doesn't have any other element pointing to it, and thereby this is empty. So so if you take the example of B points to C. So then we have B pointing to 3, which is C, and B is pointed to by A, so which is 1, and so on and so forth for C. So this is like a multi-dimensional representation of a graph, and you have encoded both all the nodes in the graph as well as all the edges in the graph using the direction of the edges. So that's important to know, that how has this been represented. A simpler representation is called an edge set representation, which is pretty much saying that you could represent all the possible edges, right? So basically saying that from 1 to 2, you have a link. So 1 points to 2, 1 points to 3, and 2 points to 3. So essentially saying that 1 points to 2, 1 points to 3, and 2 points to 3. So this also kind of covers all the encoding of the graph. You would still need a mapping from 1 to A, 2 to B, and 3 to C. So assuming that is already given, you can represent in this way. And the third is an adjacency matrix representation, which is easier to understand, wherein you would have so you would basically have a row, right, which represents the elements to which a link points to, and a column which represents the elements from which the link is, right. So this can be set of sources, right, and this can be a set of destinations. So if there is a edge from 1 to 1, so then the semantics are that this will become 1, right, because there's no circular edge. So 1 to 1 is 0, but 1 to 2 there is a link, right? So 1 to 2 there is a link, so this is 1, and 1 to 3 there is a link, so this is also 1, and so on and so forth. So 2 to 1 there is no link, 2 to 2 there is no link, but 2 to 3 there is a link, and so on and so forth for 3 as well. So essentially, if the graph is pretty dense, then this is a good way to represent it. If the graph is sparse, which means that there are very few links and the nodes are large, then edgeless representation is often used. So these are the two major representations that are used, edgeless and adjacency matrix. Usually I haven't seen this edge set representation being used a lot, right? I guess this probably is just easier to represent and use it in code. Probably that might be the intuition behind using the edgeless and adjacency matrix mode. Then I think the next part, which is interesting to understand, is that now how do you go about traversing a graph, right? Because graph traversals tend to be also sometimes pretty tricky to do, and especially doing it in an optimized manner is tricky and sometimes very, very hard to do. So if you just know the basics of traversing graphs, just basics of traversing trees well enough, then this will become kind of easy and intuitive for you. So if let's say we just take a very brute force approach of traversing a graph, then what will end up happening is that you would end up traversing the graph in a very unoptimized manner, and this would run into an exponential complexity of the number of steps you have to take. So the intuition essentially is that, let's say if you have this particular graph and you want to, and let's say there are n elements in the graph, right? So there are n nodes in the graph, and each node has this property that it has two outgoing edges. So let's say A has two outgoing edges to B and C, B has two outgoing edges to D and E, C has two outgoing edges to D and E as well. So if you want to traverse this in a brute force manner, which is the simplest possible way of traversing, at each node you will jump to each of its children, right? So when you are at A, you will jump to B and C. When you are at B, you will jump to D and E. When you are at C, you will jump to D and E, right? So eventually what will happen is that since you're taking two steps at every node, the possible combination of steps that you would have to take would become 2 raised to power n, because 2 on all the possibilities, right? There will be 2 raised to power n possibilities or n paths. So that becomes really, really slow. You would still end up traversing everything in the graph. So that will be guaranteed, and you will visit each node. But like the trouble is that you will end up running into very low complexity. And the other trouble is that you would end up running into cycles as well. So you would end up probably running into loops, because let's say if you went with, so this is an acyclic graph, but if this was also a cyclic graph, so if D had an edge back to A, then when you visited D, you would jump back to A and the whole cycle would keep repeating, right? So the algorithm will never end. It will be super unoptimized, right? You'll never get a result out of it. So we usually don't use brute force approaches for graphs. There are more interesting and more intuitive approaches that are used to do graph traversal. And one of the most common approach that is used is called a breadcrumb approach, which is pretty much saying that the basic idea is that as you're traversing through the graph, just mark every node that has been visited, right? So the way you kind of, if you like, idea is that if let's say you're going on a new path and the path is pretty like a maze and you kind of get lost in a maze, you basically leave breadcrumbs to remember which paths you've already taken in a maze, right? So that's the kind of underlying intuition behind it. And the idea is that you do the same with this approach. And the way this is done in a more of a depth first manner, so that you don't end up spending so you don't end up spending cycles in going through all the paths. You can go through one path at a time, right? So I'll just quickly jump here and then try to show this as an example, which is so let me see if this is being shared or not. Okay. Yeah. So yeah. So let's say this is the graph. I hope you are able to see it. So let's say this is a graph which is A, B, C, D, and E, right? And you want to basically traverse this graph, but avoid the exponential traversal complexity, right? So the idea essentially is that the way we do it is that we start off with something what we call as fringe nodes, right? So fringe is pretty much on nodes that occur on the boundary of the graph itself. And what we end up doing is that we start from these fringe nodes, and then we jump to the next nodes or the children of this set of nodes, right? So the idea is that you start with A and you mark this A as already being seen, right? So this the green mark basically says that A has been seen, and I'll now jump to the next set of children. So the next set of children here would be in the step 2, you could see that A has already been seen, and now we have gone to B and C and marked B and C, both of them together. So this is not a depth first traversal, this is more of a breadth first traversal, but essentially the idea is that every time you're visiting a node, you mark it. And when you go from step 2 to step 3, you will go to D and E, right? Because D and E are the children, and you will mark D and E as seen as well. So when you jump from C, to D and E, you will basically say that we've already visited D and E because we've already left these marks, so thereby we don't need to traverse them again. So that reduces the amount of inefficiency in your algorithm because you are remembering some state, right? So that's the idea behind this breadcrumbs approach. And that improves the overall kind of complexity of the algorithm, right? And within this, one of the approaches that are used is and I'll go through some pseudocode to explain how certain approaches are used. So one of the approach is a pre-order traversal approach. So we'll just go through that. Right. And it is visible. Yeah. So the idea is that of a pre-order traversal approach, which is just using this breadcrumbs approach of marking nodes and then moving forward. And in an algorithmic view, this is what ends up happening, right? So you've basically given a pre-order traversal for a graph which is represented by G and a set of nodes which is represented by V. And you can imagine this set of nodes being the set of nodes that are the source for this particular traversal, right? So the problem here is that you're given a graph and you're given a set of nodes which from which you want to figure out all the other nodes that can be reached in this graph. So imagine like you're given, for example, you're given a set of houses in a network and you want to figure out which set of houses are like you can visit from these set of initial houses, right? Or if there are a few cities, you want to figure out which cities can be visited using these particular source cities. So this is pretty much the set of sources, and this is the whole graph representation. And in this, what you end up doing is you basically you basically do a few things. So first is you figure out if the node V that you kind of started off with, if that is unmarked, then you basically mark that node and then visit it and basically go and repeat the whole process for all the edges in from V to W, right? So let's take a concrete example that will give a better idea. So essentially, let's say in this particular graph, you were given that you need to figure out what are the set of nodes that can be visited if we just start from A, right? So that's the question. So the algorithm basically says that you can start by visiting A, right? So you just mark A as something that you've seen. Then you do the visit operation, right? So the visit operation could be just figuring out any characteristic of A. So let's say in a real world problem, it could be a number of people that reside in a house, or number of like the population of a particular city that you want to figure out as a source city. So you do the visit operation, and then the next thing is you look at each of its children. So you look at the child B and you look at child C, and you then do the same operation using B as a source and C as a source, right? And what this guarantees is that for every node, right, you will be able to visit that particular node and you will be able to visit all its children, right? So those are the two invariants that it will guarantee. And there's another invariant that will guarantee is that you will not visit the same node more than once, right? So three invariants. So the first is that you will be able to visit that particular node, right? You will be able to visit all its children, and you will be able to ensure that you don't visit the same node multiple times. So if you assume that these three invariants hold, um, you can reason that all the nodes in the graph will be visited at most once, which are connected to that node A, right? So that's what will end up happening in this. And this is a simple algorithm that can help you out in visiting all nodes from starting from a given node in a optimized manner. So like the overall complexity will be of the order of n plus m, which is not exponential. So it will not be exponential. For us, that is the most important thing to know, right? And then there are certain problems in which the constraint may be that you want to reach all the nodes in the graph. So maybe you're given a large country, right, and that you want to figure out just figure out all the characteristics, like the population of all the cities. So you want to kind of visit every city, right? You don't want to just visit a set of cities that can be visited from one city, right? So how do you do that? So the way you do that efficiently, right? How do you do that efficiently is the question. The way you do that is you use the same pre-order traversal idea, but you iterate through all the nodes of the graph, right? So so the idea here would be that uh, let's say the algorithm is called pre-order traversal OR, and you're given a graph G. So what you will do is you'll iterate through all the nodes of the graph, mark them all of them as so initially you'll mark all of them as not visited, and then for each node in graph you basically do the pre-order traversal, which we've done, right? So this is slightly not correct. Actually, the algorithm should be something like this, and you would end up saying, yeah. Yeah, this would be right. So what you'll end up doing is you'll first mark all of them as not visited, then go through each node in graph and do a pre-order traversal. So pre-order traversal will be just the same algorithm that we talked about initially, but here you will assume that each node or each node in the graph could be a source node. But that is the only difference from the original algorithm. But the intuition here still remains the same, that you basically mark every node once you visit them, and you don't and you don't visit the same node multiple times. So that is the whole idea, and we should be able to efficiently visit all the nodes and also do a complete traversal of the tree, right? So this is just a very small improvement over what we've kind of discussed before. uh, so this is pretty much the two algorithms that we kind of discussed are subset of a technique that is used to visit all the nodes in a graph. One of the problems that I wanted to discuss during this course was just discuss this problem of a topological sort, right? And so one of the questions is that what exactly is a topological sort, and what does it actually mean, right? So let me just share my screen again. Right. So yeah, so the idea of topological sort is kind of interesting, and the idea is that if, let's say, there is an inherent ordering within the graph, right? So let's say if it's a family tree and you want to kind of lay down the family tree in a more flattened way, so you want to write them down, like write the ordering of 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 all the members of the family, but you want to ensure that within the ordering that you lay down or within the ordering that you print, parents should always come before children, right? So that is one constraint that may be required, because you want maybe some priority to be given to parents before children, right? There could be some problems in real world that require that. So how do you end up doing that, right? How do you uh, uh, visit all the nodes? How do you visit all the nodes in a graph and also keep the ordering in place, right? So that's the question, and we'll discuss how is that solved. So the idea is that, let's say you have a graph, right? So you have a graph G which is given with this, which basically says that there is a node from 5 to 2 to 0, and there is sorry, edge, and there's an edge from 4 to 0 and 1, and there's an edge from 2 to 3 to 1, right? So that's how it is represented. And let's take the edgeless representation for this, right? So let's say 0, there is no outgoing edge from 0, there is no outgoing edge from 1. These are the leaf nodes. There is 1 from 2 to 3, from 3 to 1, 4 to 0 to 1, 5 to 0 to 2, right? Just encoding this as an edgeless, right? The representation we talked about. Now, how do you go about traversing this, right? So one of the intuitions behind being able to traverse this, keeping in mind the topological ordering, right? The ordering in the graph is to assume that you, if let's say you had a way to go backwards from each of the leaf nodes. So let's say this is this is a root node, this is a root node, because like pretty much nothing comes into these nodes, and let's say this is a leaf node and this is a leaf node, right? So the idea, one way to understand is that if you're able to visit, do a reverse traversal from the leaf nodes and print each of the elements in the opposite order. So let's say if you're able to say that I will we'll do a depth first search, which means that you'll first go into the depth before you go broadly. So if you are, let's say if you start from 1, and if you can figure out that 3 lies above 1 and 2 lies above 3, so let's say you're able to know that, and you're able to print it in a way which is 2 before 3 before 1, right? So you start with 1, but you go back to 3 because 3 is a parent of 1, and you go back to 2, which is a parent of 3, and then you print in this particular order, right? This order will always preserve the topological ordering. So pretty much that is the whole idea. So I'll try to repeat it again. So the idea is that if, let's say, you take this graph, take all the leaf nodes and move in an opposite direction, right? So right? So basically go from child to parent, and then print the parent first, right? So that would ensure that the topological ordering remains preserved. And the reason is that what you're trying to do is that for any parent-child relationship, you're always keeping the parent first before a child, right? So for this particular relationship, you're saying that 3 should come before 1, and for this particular relationship, you're saying that 2 should come before 3, and you're going in a depth first manner. So if there was a parent for 2, then you will go from here and then say 5 should come before 2, and so your ordering will become 5, 2, 3, 1. Right? So that's like the intuition. Of course, it may not be completely clear, but that is the basic intuition. And as we've been kind of discussing this intuition, you can imagine that if you go in an opposite direction, one of the data structures that could be used is a stack. Uh, and the reason for that is that a stack is a LIFO data structure, which means that the element that comes in the last, right, goes out first. Which basically means that if you start from this, if you look at the output, this is the element that has been traversed first. It has to go out the last, right? So I mean, you can also say that the opposite of this should also be true, that the one that comes in first should go out the last, right? Although this is not the standard mechanism, but it's a way to understand it. So if in this traversal 5 is something that comes in the last, it should go out the first, right? So that is the intuition that we discussed, and stack gives us a good idea, or like is a good representation of it, right? So that's why we are using stack. So essentially, if you're able to like match these intuitions, right, saying that this seems like a use case wherein a LIFO ordering is required, a LIFO ordering is used by stacks, and thereby we should use stacks, right? So that's how people are able to connect the right data structure to use, which is usually the crux of the problems that we end up running into, right? A lot of people are not able to guess that this should be using a stack. But keeping that aside, if we already know that we need to use a stack, right? And then the way to kind of go about it is pretty much very simple. So the way you can go about it is that even if you take this set of edge list, right, and you go in this particular direction, which is saying that 0 is pointing to null, 1 is pointing to null, and 2 is pointing to 3. Even if we go in this direction and keep all the keep pushing all the elements into a stack, right? So let's take an example. I think that might be easier to understand. So let's take a traversal order wherein we first see 0 and push 0 onto a stack. So this is a stack representation, and these are the number of steps in the stack, right? So you see 0 and we push 0 onto the stack, and then you go to the next node, push that onto the stack, go to the next node, and until you find the end of the set of nodes that this particular node points to, you don't push this on the stack, right? So basically what's happening here is that 2 is the parent of 3, and you would not push 2 until 3 gets pushed in, right? And all the children of 3 get pushed in. So so let's say we go with 2 and we see 3, so we push 3 first, and then we go with 3, push 1 again. But since like 1 has already been seen, so just using the breadcrumbs approach, we don't do anything with it, right? And then we push 2, and then we go with 4, figure out that both 0 and 1 have been already pushed onto the stack, so we push 4, and then we push 5 onto the stack because 0 and 2 have already been pushed, right? So this is a slightly different approach than we discussed, but the idea for this implementation is that we do a depth first traversal. So the idea with the depth first traversal is that you keep going to each children until you hit the end of the set of children, right? And you push the children before parent, right? So that is the idea. So let's write them down. So one is that we do a DFS, which is basically saying go to so basically go to children unless all the children have been seen. So that is one, and the other is, so one is DFS and the other is basically push children, right? So push children before pushing the parent into the stack, right? So that is if those two constraints hold, and which is this algorithm that we'll implement in a code form. If these two invariants are kept, then what will happen is that um, since you've pushed parents after children in the stack, the parents will always come up, right? So essentially what we were saying was that um, before we push 5, we will ensure that 0 and 2 have been pushed onto the stack. So that is the case here. Before we push 4, we will ensure that 0 and 1 have been kept in the stack. So that is the case here. Before we push 3, 1 has been kept in the stack. So that is the case here, and so on and so forth. So if the parent are at the top of the stack, of course, when you pop them out, right, or when they come out of the stack, they will be in front, right? Because now the ordering that will come out will be 5 and then 4. I mean, essentially the ordering will be like this, right? So 2, 3, 1 and 0, which is what is expected, right? So essentially the underlying ideas are two. Like pushing children before parent is pretty much coming from the fact that you want to keep this partial ordering within the graph, and DFS is to ensure that you are able to discover all the children before you push the parent. Because if you don't do DFS, then the trouble is that you might go from 2 to 3 and you may not be able to look at the children of 3, which could result in issues, right? Because 2 has to come before all the possible children of 3 and the children of 3 and so on and so forth. So those are the two ideas that are used. So if you just look at the problem of topological sort and are able to reduce it down to two major ideas, one is that you have to go depth first, and the other is you have to keep parent always above the child. You should be able to reduce it down to this particular algorithm. And it is slightly complicated. You probably have to do more problems like this to be able to get to it. Like, I mean, even I don't remember it on top of my head, but as I was doing this exercise, now I kind of understand the intuitions better, right? Okay. Yeah, it can. We can discuss a little more if there are doubts around it. But yeah, I mean, just getting those two basic ideas in can also, like, even if you're in the interview setting, if you just give those basic two ideas out, then I think like even the interviewer would help you out in getting to the right algorithm eventually. But I think if you don't get this, then I think like the problem is lost. So what I did was that for this particular session, I didn't end up coding it. The algorithm is a bit long. Let me just share my screen. I'll go through the code itself. Uh, and if there are any doubts, let me know. But I'll try to just go through the code. That was what I thought could be done. Right. So this is the code of topological sort. This is available on Geeks for Geeks as well. I think the toughness is not in the code. I felt the toughness mostly in understanding those two intuitions and then mapping it down to the right data structures. So in this particular algorithm, what we end up doing is we have basically a graph structure defined. So the graph is essentially consists of a class which has a set of nodes. So this is the number of nodes or number of vertices in the graph, and we represent edge list, right? The idea is just use edge list to represent the graph itself, and and the edge list is represented in a way wherein for this particular list, the index of the list is the index of the node, which is the source. So let's say if you are going into the 0th index of the list, which is the first element of the list, then that will be the first node in the graph. So let's say that is A, right? So it will become A, and all the nodes in which are the values in this list will be the nodes which are children of A. So that's how it is represented, and that's how this is very common, or the standard way of representing edge lists. It's just that they have kept index as a pointer to the source node. And then they have defined a topological sort util, an add edge util, and a topological sort method. So the topological sort method is a top level method. There's nothing much logic here. The most of the logic is in topological sort util, and they have an add edge method which basically builds this list. So if we look at the graph, they have this add edge method, which basically says that add an edge from V to W, right? Which is from node V to node W. So this is the source and this is the destination. So you can see you put it into the source and the destination, and each node is accessed by a certain index. So that's how it is represented. It's an easy kind of way of, very intuitive way of representing a graph, right? So we start with what is done in topological sort, which is pretty much the parent method, and then we'll go into this helper method. So the parent method, basically what it does is that it first marks all the nodes not visited, because this is the start of the algorithm. You've not seen anything, so you mark everything as not visited. And then what it does is that it goes through each node in the list and tries to do a DFS for it. So the way it does a DFS is by calling topological sort util, and it also ensures that this node has not been visited, because if it has already been visited, then there's no point visiting it. Otherwise, you'll run into loops, so you can't do that, right? And in the end, what it does is that it just in the reverse manner prints the stack, right? So once this part of the method completes, your stack is built. So this is the first step. We can see this is the first step and this is the second step. This builds the whole stack, and after this, it basically pops elements from the stack and prints it out. So most of the core logic is in source topological sort util, which basically what it does is that it will basically look at each node and look at populate the current stack with the node that has to go in, and also it needs to know about the visited set of nodes. So that's why these are passed. But the idea is that you look at each one node at a time, right? So, and this I think is the node which is the source. So that's how this is called. So what you end up doing is that you mark this as visited, because now you have processed this particular node, which makes sense. The whole logic is pretty much encoded here. So what you do is that you look at each of the elements of the list, which is basically saying that for each parent, look at all of its children. And if a child has not been visited, then call the topological sort util again on the child. So a depth first algorithm is usually represented using recursion. And this is a mechanism of recursion, right? So as we were also in the one node, right? Sorry, in the node that we had, as we were kind of visiting each child, when you visit a child, you assume it may be a parent of other children. You again visit the children of that child, right? So that is the recursive idea that has to be encoded into this algorithm. So thereby, what ends up happening is that you assume V is a parent, look at each of its children, and then assume that each of its children are also a parent, and so you keep visiting them. And once you hit all the children, then you push the parent onto the stack, right? So that's the idea, that keep iterating through all the children. Once you've iterated through all the children, push the parent onto the stack, because what would have happened when you are here is that all the children would have already been pushed onto the stack. So I think recursion is something that is usually tends to be very tricky to understand when you're very new to coding, because you can't like visualize how the multiple steps are folding and unfolding, right? There are two steps to it. We'll try to cover that as well, probably sometime later. But the idea is that you can assume that by this step, all the children of V would have already been pushed onto the stack, and so the parent can be pushed now. So if you get that intuition, you should be able to write the algorithm correctly. Although just writing this algorithm in the first pass is tricky, and I would say it's also hard. It's not easy to just write it right off the bat. You would have to kind of go through it a few times. And then once you've done this topological sort util, which means that all the stack has been populated with depth first approach, and also keeping the parents above children, you basically pop them out, and while popping, the order will be reversed, right? So the graph that we discussed in this note is pretty much the same. So I just try to run it, although this should not fail, because I just copied it, so I haven't written it. But essentially what it does is that it will basically print 542310, and if we see it in our so let's just see it back. Right, so if we see it in this, so 5 and 4 are parents of everything else, so they have to be printed first, and then you would need to print 2 and 0, and then probably 3 and 1, right? So that should be the ordering. Just want to check. 3, 1, 0. See. Yeah, so the graphs may be a little different, I think. 1 and yeah, so that's fine. I think that's fine. So the 5 and 4 are parents, 0 and 1 are leaves, so they can be at the end, and 2 has to be before 3. So essentially, and 5 has to be before 2. So the right ordering could be 5, 4, and they can be multiple ordering. So it's not necessary that there has to be one ordering. So 5 and 4 have to be above. Then you can have 2, you can have 3, you can have 1 and 0. So 1 and 0 can be inter-replaced, so that is okay. 5 and 4 can also be inter-replaced, that is okay, because there is no ordering in between them. And 2 and 3 cannot be, so this has to be in the same order. Yeah, and this also has to be an order. So they can be multiple orders. You can also have 4, 5, 2, 3, 1, 0, 4, 5. But that doesn't matter, 0, 1, there can be multiple ways, but at least one ordering has to be right? So that's the idea. There is one more problem. I think I didn't cover it and I didn't prepare for that particular problem, which is given a graph, how can you find the shortest path in the graph? And that is covered by a very famous algorithm called Dijkstra's algorithm, which I think is a little more complicated. So we can you can try to go on your own. I have shared it in the notes as well. But I think the idea here was just to gain some intuition onto there are structures, data structures called graphs, and you can do traversals on graphs using certain mechanisms, and you can do it very efficiently. And what are the intuitions behind that? And you can also see another interesting thing, that the data structures that we've been learning before, for example, stacks and lists, and depth first traversal in a tree, they are kind of, all these concepts are now compounding and getting used in one data structure, right? So that's how the fundamentals are built. When you first if you are clear with the basic algorithms, then you can understand these more complex ones a little more easily, right? So that pretty much concludes today's session, that I wanted to cover things. If there are any questions, let me know. I can try to cover it again. So question is that, but 4 has only 2 children, that is 1 and 0 in this, right? So 1 and 0, right. But you can still see that 4 is before 1 and 0, right? 5, 2, 3. So even 5, 2, 3. So you're saying 5, 2, 3, 4. So 5, 2, 3. Yeah, I mean, that could also be in order. So even 5, 2, 3, 4, as it's satisfying. Yeah. So that could also be in order. So like 5, 2, 3, and then 4, 1, and yeah. Even that could be. I mean, there can be multiple orders, Suraj, of how topological order can be satisfied. So there is no unique one. So essentially, what you need to do is write an algorithm that can give out a correct sort order, right? You can write it down in different ways as well. Yeah, but need not be a unique property. So that is definitely there. So that is pretty much it, what I wanted to cover. In the next session, I just wanted to give a very brief idea of if any of you are preparing for interviews, just within an interview setting, what are the things that are useful to do? I thought that could be useful to cover. Within this series, I just wanted to cover a few data structures. So I've mostly done 8 sessions here, and I'll ensure that all of them get uploaded onto YouTube. After that, I wanted to uh, uh, do a few more advanced data structures, but that might take a little more time to get to preparation of it. And I also want to give some exercises as well. The next time I do the same exercise or same set of sessions, so that people can also take time out to do some of the algorithms. So that could also help them out. Yeah. So if there are any questions, any feedback, let me know. I'll share the notes as well. So the notes that I went through, I also did the same for hashing as well. I don't know if everyone received them, but I'll do the same for graphs as well. So that if you need to take a pass, you can quickly do that. They are pretty kind of constructed notes. Okay, I hope you all enjoyed the set of sessions. I got to learn a lot just by doing these sessions. And I also thought that some coding platform would be useful. So that is something I want to give out as a next in the next set of sessions. But other than that, it was really helpful for me, and hope you got to learn something useful out of these as well. Okay, cool. So I'll kind of call it a meeting then. Thank you.